All right. Here we go. First question. Bring it. Tell your neighbor. Correct answer is B, Buster Brown. Everybody goes that? Based on pre-quiz. Okay. So the slower it goes, the higher the index of refraction is. Yeah. Soon. I had my last kid take it today. There's last student who was absent. I could figure that out, yes, but I don't remember. So disappointed. Yeah.
Is it in Power School? I got like a good grade on the last one. Someone still has to take a test?
I just finished it today. Okay. Correct answer is? Correct answer is A.
I think I really did that. The fastest light for the least amount of refraction for light is vacuum space.
Yep. Yep. All right. One.
That's what I thought. I guess
Okay. So.
What's a fish tank?
Smoke in a can. Smoke in a can.
That's how my
Ooh, I don't know if this is gonna pick up. We're gonna see what happens. Video, folks, you might be in the dark. Okay, this is proof of concept. I'll do this a couple times so people can see throughout the room. Oh, we're good. We're good. We're good. All right, folks, on this half, this is for you.
Is it gonna stink? No?
It's hilarious. No one's ever asked me that before. All right, so going from air into water. Okay, you see how it's bending? Going from air into water. Everybody see that? Okay. For a video audience. I don't know. You can see that. You can sort of see it. Air into water. Okay, see it bending? And air, ooh, that was ripply. Air into water. Apologize for the crazy ripples. Air into water. Good with that? All right. Yeah. Dr. Carlson got it. I don't know. Just look up Fantasy FX. Oh, Dr. Carlson also got that. Probably eBay. Not eBay, but Amazon. All right. So. So. So light goes in. Okay. Light is a wave. And so the analogy is it's a wave. So think of this laser as wave fronts, kind of like how waves crash up on an ocean. Okay. But the analogy we're going to use is rolling in a wheelchair. Okay. So pretend like here we're looking down on top of the person in the wheelchair. You're in a wheelchair. Here are the wheels. Here are your legs, your arms. Everybody good? Okay. While we're going through air, it's like rolling on a sidewalk. But this is the edge of the sidewalk, and in here is grass. And so as we're rolling, this wheel gets in the grass first. And if you're continuing to push, what's going to happen to the speed of the wheel in grass? Speed up, slow down, stay the same. It's going to slow down. But you're still pushing the wheel that's on the sidewalk. What's going to happen if this wheel is going slower and this wheel is still going the same speed? You're going to end up turning until both wheels are now in the grass and there's no more turning going on. Does that make sense? So this is why light changes direction when it changes speed. Most people are okay with the fact that light changes speed when it goes into different materials. That's usually not hard to convince people of. Like, okay, it's thicker or whatever. But changing direction, that's kind of counterintuitive because every time you hit the gas pedal in your car, it's not like you're like, or like hitting the brakes like you don't, changing speed isn't associated with changing direction. But this is why changing speed for light, for a wave, causes a change in direction. Good with that? Tell your neighbor. Correct answer is? Correct answer is A. As it goes from slow to fast, it speeds up. Slower means a higher index of refraction, and it bends away from the normal line. Okay? At this point in time, you're just kind of regurgitating the information that was presented on the pre-quiz. A is the correct answer. Okay? My hope is by the end of this lesson, you'll have more of an intuitive feel for why this is. Okay? Tell your neighbor. Correct answer is A. Okay? Real quick, just to like make sure we're all on the same page. Here's the surface. Here's the normal line. Okay? Going from air into water, you're going from a low index of refraction to a high index of refraction. And you're going from fast to slow. It's going to bend towards the normal line. Okay? Here, B is the no refraction, straight through. Towards the normal line means you're going towards this. Away from the normal line means you're going away from this. Good with that? JP.
So air and water reflect here, then it would be C.
And the ray of light, yes. Yep. Mm-hmm. Sure.
Is it possible for it to be no refraction? Like, will there be like several? Is that possible?
Yes. Yeah, if, let's say we had, there's a substance that has a close index of refraction to water. I was going from that substance into water, there would be no refraction. Good question. Good with that? I'm just going to tell you. This is a factoid. This is based upon one of the things I said early on in this unit. When you're measuring angles for this chapter for light, we are always measuring the angle from the normal line. Always from the normal line. Okay, correct answer is A. There we are with that. I've seen all of these B and C. Don't be that person. Measured always from the normal line. Okay. Tell your neighbor. C. Here we go with that. Bending away from the normal line, going from a high index of refraction to a low index of refraction. It bends away from the normal line. Okay. Going from slow to fast, away from the normal line. All right. So here, looking at the wheelchair analogy, going from air into water, you're going fast. So it's going on the sidewalk, and then going into the grass. This wheel is going to turn first, slow down, bends towards the normal line. Here, you're going through grass, and you're going onto the concrete, onto the sidewalk. This wheel is going to speed up faster, sooner. And then once they're both on the sidewalk, they stop turning. Good with that? Okay. My strategy is to give you two ways to remember this. One is the wheelchair analogy. Secondly, if you can just take a snapshot in your brain of this demonstration, I have this locked in, like it bend away towards my brain starts here. So just trying to give you ways to remember it. Again, I'll do this multiple times. So here, going from air to water. Okay. Bends towards the normal line. Going from water into air, it's going to bend away from the normal line. Okay. Now, full disclosure here, there's a lot going on. Kind of looks like a laser show. At every boundary interaction, there will be some part of the light that will be reflected off of the surface and another part that's going to be refracted into the surface, into the material. Okay. So when I do this, like if you want to see like the full on effect, Okay, there's a lot going on there. I don't care about this one. That's just reflecting off the glass. What I care about is this one. See how it's bending away from the normal line? I don't care about the part that's reflecting back into the water. Okay, good there. So going from air into water, bends towards the normal line. Then going from water into air, bends away. Does this stink?
It's not that bad. You can smell it.
Air into water, bends towards the normal line. Water into air, bends away from the normal line. Good? All right.
I love drawing.
Blah, blah, blah.
Don't look at the top. The bottom.
Oh, what did I do with that? There it is. Here come the lights. Okay. So if a ray of light goes through water and then enters glass at an angle of 28 degrees, what is the angle of refraction? Well, not component. It's easier. All right. So we have our boundary layer. Okay, let's just say glass is on top, water's on bottom, just to mix things up here. So light's going from water into glass. There's our normal line. The 28 degrees is that angle there. Before we do the calculations, hypothesize, is our calculated angle of refraction going to be more or less or the same as 28 degrees? Tell your neighbor. More or less or the same, 28 degrees. Yeah.
But that is.
So over here, and See, you good? Okay. All right. So everybody have a hypothesis. We're going to find out if your hypothesis is right or not. So we're using Snell's law. I kind of like the German version, Schnell law. Just more fun to say, more aggressive. Okay. So it starts out in water. Angle of incidence is 28 degrees. Ends up in glass. And we're looking for theta 2, index or angle of refraction. Make sure you're in degree mode. Then do inverse sine. You get 24 degrees. How does that compare with what you hypothesized? Okay. As going from low to high, from fast to slow, it bends towards the normal line. That angle there is 24 degrees, bends towards the normal line. Good with that? Or always. Yep. With light. Good there? That is the extent of the math. Okay. I'm just going to tell you. Correct answer is A. When you go straight into one material to the next, you can't get any closer to the normal line than you already are. Okay. In the wheelchair analogy, you're going straight off of the sidewalk with both wheels into the grass at the same time. So there is no change in direction. You do change speed, but you don't change direction. Okay. This is true for going from high to low, index refraction, or from low to high. Doesn't matter. Anytime you're going straight into a material, 90 degrees, no refraction. Okay. Tell your neighbor. Correct answer is C. Okay. Here is why. The greater the contrast, the greater the difference in indices of refraction, the greater the change in speed. Okay. In the wheelchair analogy, this is like going from the sidewalk onto a gravel road. From the sidewalk into grass. From the sidewalk into sand. Have you ever tried to ride your bike through sand? Didn't go very well for me. Every time I've tried it, like slow way down. So as you go off your wheelchair, one side goes into the sand. It's like you get this crazy change in direction because of the difference in speed. Nope. Oh, got it. The change. Yeah. The most bending. I do see what you're saying. It'll make this will make theta 2 the smallest. Good call. But the greatest change. So I should probably rephrase that question. Okay. What I want you to do you're gonna partner up. Everybody needs a cup. They're wet. It's just water.
They had to be ready because I think I might be able to box against you guys because you have the rotation without me. So she was like, I just like I wish we could have like hard minutes.
You catch well. Rachel, is that it? All right. Here's what you're gonna do. One person is gonna take the cup with a dot in it. And they're going to orientate that so that, actually, I'm going to do this first. One person going to take their cup, they're going to fill it up with water. 3/4 full. These nozzles are aggressive. Don't like, okay. Another person is going to put their cup on a table on a desk. There's a black dot. You're going to rotate the black dot away from you as far away as possible. Then you're going to, oh, where are you? So, there you are. You're going to move away until that black dot just disappears below the rim of the cup. And then the other person with a full glass of water is going to pour their cup, the water into the cup, and magic happens. Okay? And then repeat, like switch roles and repeat. Go. Once you're done, you can empty your water. Put your cups back over here. There are 8 sinks in here. Lots of options. Get water. So, before you poured water in, your dot was reflecting light off in all directions. Does that make sense? Okay. Light from that goes over your eyes. Can't see it. Light that would have hit your eyes is hitting the rim of the cup, so you don't see the dot. Okay. Can't see the dot. Then you pour in water. Again, your eyeball is the receiver, the catcher of light. It's not the emitter. Light is starting in the water and going into air. What happens when light goes from the water into air? It bends away or towards the normal line? Away from the normal line. Okay? So, here's the normal line. It bends away from the normal line into your eye. And you think, you do see the dot. And you think you see the dot right here. This is known as apparent depth. Okay? You think you see the dot located right there because we assume light goes in straight lines or in straight paths. Okay? When I see this marker sitting on the desk here, I assume it's there. Like when I go to grab it, I'm not going to go like, I'm right there. It is where I see it to be. Okay? That works out great so long as the light isn't changing mediums. If light changes mediums, where you see it to be isn't necessarily where it actually is. Okay? You guys ever read The Hatchet? Classic book. Tell your neighbor.
Are you aware? Okay, so the opposite is white is where the
Correct answer is A. Okay? Light comes. Remember, your eyeball is the catcher, receiver of light, not the emitter. Light comes off the fish refracts, bends away from the normal line. You think you see the fish. Straight line pass. Right there. Tell your neighbor. Everybody good with C? You think you see the fish here. It's not actually there. It's below that. Okay? Last question. We always think about what we should do to see the fish, but what about the fish's point of view? I mean, no one ever asked, what does the fish see? For the sake of time, remember the eyeball is the catcher, the receiver of light. So light's coming off of this spear. Wow, that's going to be aggressive. Light's coming off of this spear, refracting towards the normal line. The fish sees the spear there, above where the spear actually is. Good with that? Okay. No homework this weekend.